Hey everyone, welcome to This Explainer. Today, we're diving into an incredibly fascinating paper that tries to do something pretty wild, bringing the step-by-step logic of artificial intelligence into the messy, highly physical world of engineering design. I mean, if you've ever watched a large language model reason its way through a problem using a chain of thought, you might have caught yourself wondering, could human engineers apply that exact same structured reasoning to complex physical systems? Well, that is the core premise of a methodology known as the chain of design. Okay, let's dive into this. Here's our roadmap. We're going to start with the messy reality of design, enter the chain of design methodology, walk through the six-step iteration loop, look at the math of convergence, navigate the Y-chart domains, and finally, discuss engineering in the AI era. Section 1. The messy reality of design.
So think about this. How do engineers actually navigate the chaos of building complex systems? You know the drill. You're constantly balancing competing objectives: efficiency versus transient response, speed versus stability, cost versus performance, all while juggling unpredictable environmental uncertainties. It is almost never a straight, clean line from initial requirements to a finished product.
And there's this great quote from our source paper that really hits the nail on the head. Engineers seldom arrive at a final architecture in a single attempt. Assumptions are revised, parasitics are uncovered, models are corrected. The absolute truth here is that iteration itself isn't the bad guy. The real problem? Unstructured, untrackable iteration. Look, if you change 5 variables at once and your design suddenly improves or completely breaks, you don't actually know why.
Section 2. Enter chain of design. Time for a paradigm shift.
We desperately need a way to make progress predictable and explainable. Enter the chain of design, or COD for short. This is a sequential, highly iterative framework. So the crucial point is that each design stage isn't just a random educated guess. It's explicitly derived from first principles, strictly evaluated, and refined through feedback. Much like an AI breaks a prompt into a reasoning chain of smaller verifiable steps, COD asks engineers to turn iterative design into a rigorous, trackable chain. This whole methodology rests on 5 core pillars. You move through incremental reasoning, always leaning heavily on first principles analysis. You utilize failure-driven improvement, integrate feedback, and aim for convergent optimization. And I love this part. In this framework, failure is a highly successful data-gathering step. A failed iteration is incredibly useful if it isolates a specific mechanism, like, say, a pole dominating your phase margin, and then yields a corrective direction. It's all about taking narrow, testable steps that look a lot more like controlled experiments. Section 3. The 6-step iteration look. Okay, so what does this actually look like in practice? Let's walk through the micro-level reasoning sequence. Step 1. State the target as a testable checklist. Step 2. Find your dominant bottleneck. Step 3. Build the absolute smallest model that predicts that bottleneck based entirely on first principles. Step 4. Propose a single architectural or parameter change. Step 5. Evaluate and document it. And Step 6. Integrate that feedback into reusable knowledge. And here's the secret sauce to making this work. To avoid running in circles, every single loop must end with a tangible artifact, a new minimal model, an evaluation report, or even a quick postmortem. You absolutely have to leave a paper trail of your reasoning.
Section 4. The math of convergence.
Now, if you do this right, design stops feeling like a guessing game and starts acting like a mathematical optimization problem. You're basically treating design like gradient descent. Take a look at this equation. Your next design state, d of k plus 1, equals your current state minus your expected improvement plus your real-world feedback. That alpha term? That represents the principled improvement you expect from tweaking a variable, like increasing transconductance to boost loop gain. But that beta term is the real-world feedback knowledge. That is reality hitting your model. It's the sudden discovery that your stability is actually being ruined by a packaging parasitic you totally didn't account for.
Now, what's really interesting about this slide is how we can map that abstract math directly onto a familiar engineering concept, a closed-loop control system. You have your target specification, you compare it to your current performance, and the resulting error feeds straight into a design controller, which then spits out your next design update.
But who is actually operating that design controller? Well, in the modern era, it's a supervisory control architecture that pairs human reasoning with AI reasoning. It's a brilliant dichotomy. Humans bring the physical intuition, the first principles understanding, and the constraint interpretation. Basically, we provide the stability. AI, on the other hand, brings pattern discovery, vast design space exploration, and rapid hypothesis generation. It massively expands your exploration bandwidth, while the human expert ensures you don't confidently drive the whole project off a cliff. Section 5.
Navigating the Y-chart domains.
And this brilliantly illustrates how we zoom out from those micro-level equations to the macro blueprint of the classical Y-chart. In traditional top-down design, it is so easy to fall into local optimization traps, making something absolutely perfect in theory that is literally impossible to build physically. Well, Chain of Design prevents this by synchronizing multi-domain reasoning right in the center.
You are constantly oscillating between these three domains. For instance, say you have a failure in the behavioral domain, like you fail a measurable transient load test. That immediately triggers a hypothesis in the structural domain. You think, aha, I need to modify my compensation network architecture. But wait, that structural change is instantly checked against physical domain constraints. Does this new capacitor physically fit on the layout without introducing some massive parasitic pole? Every single iteration replaces the current bottleneck with a new one, until you finally meet your specs, with margin.
Section 6. Engineering in the AI Era.
So how does this all fit into the broader landscape of modern design frameworks? You're probably familiar with the big ones, and they all have their place. CDO is fantastic for lifecycle execution. The double diamond model is incredible for divergent innovation and breadth-first exploration. Design thinking is totally on match for human-centered problem framing. But Chain of Design? COD is your depth-first, physics-centered analytical engine.
The core takeaway here is that COD doesn't replace those other frameworks. It serves as a deep, rigorous analytical layer underneath them. It is highly adaptable and uniquely built to manage multi-objective, uncertain requirements where physical constraints dictate what's actually feasible. It explicitly logs your iterative record, separating your principled updates from feedback knowledge, ensuring you aren't just wasting time thrashing back and forth between competing changes.
Which leaves us with this final, somewhat provocative thought. AI is giving us the power to generate hypotheses and explore design spaces faster than literally ever before. But speed without direction is really just thrashing. So as you look at your own workflows, ask yourself, as your AI-driven exploration bandwidth expands, are your engineering iterations actually built on a trackable, solid chain of reasoning? Setting up that foundation might just be the key to solving your next impossible problem. Thanks for joining me on this explainer, and keep exploring.